We're going to continue the discussion on Monte Carlo methods. And today we're going to talk quite a few more methods for doing fancier Monte Carlo. Okay, they are known as Markov Chain Monte Carlos. So just a brief recap. Monte Carlo methods is to basically replace this guy with a collection of samples, right? And with that, you can really turn the often intractable tasks such as the inference task, like computing the expectation of a function, into a sample-based addition. At the end of last lecture, someone asked me, how does it relate to some of the inference tasks we often talk about, like computing the marginal probability of a set given some evidence? How this operation or anything we talk about so far relates to typical inference problems like this, or like the likelihood of data, or the value of the log partition functions, or partition function itself. How do they relate to each other? Can someone give me a hint, or you want me to explain directly? I claim that they are the same thing. They actually all can benefit from sample and using the same technique. Did you see? How do you see it? For example, this one, okay, equals to what? It equals to the expectation of an indicator function of x alpha. Do you see it? Right? So this operation basically can realize all your inference tasks relating to marginal probabilities, or marginal probabilities, conditioning evidence, and so forth. And for this tool, remember last time we established a connection between the normalization constant versus the weights of samples, right? The average weights of the sample actually correspond to the normalization constant. Therefore, basically, by getting these samples, you can easily address all the inference tasks that you run into so far. So this is just a quick review. And we also know that there are some limitations in Monte Carlo methods, mainly due to the quality of the proposal distribution Q, right? And we tried quite a few approaches, mainly to boost the acceptance rate or ratio of the samples generated by Q. We want to make sure that they are mostly accepted so that they can be better used of. And also they reflect all different regions under some strange distributions which may be multimodal, which may be mismatched with the proposal. And therefore we can weight them, we can re-weight them, we can sample the re-weighted samples, resample the weighted samples, and so forth, to really augment the Q in some way. And that actually leads to what we are going to discuss today, which is a more aggressive approach, to improve the Q. How about we're going to update or improve the Q every time we use it? Okay, so that's basically the idea behind a Markov Chain Monte Carlo. For example, here is a MCMC approach, which goes like this. We're going to, here, for example, we have a very bad distribution Q, and which is fixed. And then you are going to draw samples like this. You kind of can see that however I'm going to manipulate those samples, it is very hard to cover this part. You can still cover it because there's a long tail here, which still allows samples here to be drawn occasionally. maybe once every 10,000 examples, or maybe even less often. And then you can reweight it and resample and so forth. But it's a long shot, right? You only got to resample it once you already sampled, say, 10,000 examples or even more, right? So what if I'm going to use an adaptive queue, which is to, instead of this, I'm going to now, use the last example I draw to define a conditional proposal, okay, for drawing the new sample. Okay, so that's basically the idea behind MCMC. Okay, so the pictorially goes like this, right? You can start from one sample, the first sample, and then conditioning on this sample, you are going to define, a new proposal. You draw x2. Conditioning on this means that it's centered maybe in x1. Therefore, you get this red curve. And then you draw, with some good luck, you got a sample from the tail part, but not too extreme into tail. Then you are going to use x2 to define a conditional proposal. Float, you draw x3. And then you hopefully are now shifting the mass toward right. And then you're going to maybe get a new sample that goes even further. That allows you to penetrate this low mass barrier and go to another mode in the more complex target distribution. Right? So this is the idea of the so-called adaptive proposal. So today we're going to study how to really operationalize this idea, and also how to make sure that they are correct. Say after many samples, your samples are actually coming from the true target distribution P. So one important idea is known as the Metropolis Hastings algorithm. It basically operates like the follows. You draw a sample, x prime, from a proposal, which is sometimes known as the transitional kernel, because it is transitioning from the old example to the new one. Okay, x is the previous example, and then you have a new example. Okay, and they should again, be determined to accept or reject, and then we use this acceptance probability, which is the ratio of the importance of the sample weights. Okay, on the top, it is the importance weight, of the x prime. Okay, it is defined by the probability of this new sample under the target, and also multiplied with the transition. And at the bottom, it is the importance of the older examples. Okay. Actually, no. This is it should be like this. The proposal, the importance ratio of the target probability versus the proposal probability, and you actually compare the ratio of between these two weights. And then this ratio can be either smaller or greater than 1. Right? You could have a case where the new examples are less important than the previous ones. Therefore, you want to really take a limit, which basically means that this number should be bounded between 0 and 1. Therefore, you actually have a minimum between 1 and this ratio. Okay, meaning that if the ratio is above 1, you are going to accept it with probability 1. Okay, so this transition, this acceptance probability is going to ensure that after sufficient many draws, okay, you can get samples coming from the true distribution Px. So we're going to show how that can happen. Okay, so this is just the procedure. It's very, very simple. All you need to remember is that you have this new acceptance rate calculation for every new examples. Okay, and again, this is a kind of an imitation of a simulation of how it looked like in operation. Say, let's define the proposal to be a Gaussian centered at x. Okay, and we're going to, the target is a bimodal distribution P of x, the one we saw before. How it actually push you correctly into covering both density, both modes. Well, you start from some initial random sample, say x0. You define a proposal distribution where you can sample x1 from. Say you get a x1 this time in here. Okay, that's possible. It is actually away from our other modes in the target distribution. Although in practice you don't know it, by the way. You don't actually see the whole distribution. You only know the Q proposals. But you get this new sample. What you do is to use this new sample to define a new proposal distribution in which is now shifting to the left-hand side. And then you're going to draw x2, which we have in here. Okay, and by putting, by the way, x1 and x2 in this case, you can compute the ratio in here, and it was determined to be accepted. Okay, and then you are going to have a new distribution x q of 3 given x2, where you can draw another sample. In this case, this sample is rejected by this. Okay, and when rejection happens, what do? You're going to basically just take the older example, okay, and put it into your bag, okay, and you're going to then reuse this proposal centered at x2, now known as x3 because x3 equals to x2. Okay, and then you are going to and you can hear a little story why it is rejected, because this ratio in this case happened to be close to 0, so it is very unlikely that this example can be accepted. And then you are going to resample from this distribution and get x4. And in this case, x4 is not very likely under the proposal, but it's you're lucky you got it sampled. But it gets a boost because under the target distribution, it has a high probability. Therefore, it is having a better importance weight. Therefore, it is accepted. Right. So using this very interesting dynamics to amplify basically the trend of moving into proper modes under the target distribution, even though your proposal isn't giving you a very good chance of this one being accepted. And you're going to capitalize this success and now move your new proposal to here. Right? So that's the key. You have this adaptive proposal which allows you to capitalize a good sample and then hang on there and allow more good samples to be generated. Right? In our fixed proposal, you have to live with this old proposal all the time. Okay, and then you are going to do some additional augmentation to reweight it and to resample it, which is far less efficient than this adaptive proposal. So that's the idea behind Markov chain Monte Carlo. Okay, so you can see that even though you have a unimodal proposal distribution Q, which is just a single Gaussian centered in some places, you can still sample bimodal distributions in this case, or even multimodal distribution, because the proposal is going to move around, okay, and swipe different regions. There are some interesting aspects about this technique, MCMC. First of all, the algorithm needs a period called burn-in, which produce samples just like any other period of the sampling phase. But what you are going to do is to throw away those samples. These are bad samples, okay, not coming from the true distribution. Maybe the first 1,000 or first 10,000 examples, are to be discarded. Exactly when that happens, is a mystery, is an art, and people sometimes can do a empirical guesswork to monitor when to discard. And then we have this interesting question about why the procedure using Q of x prime given x converge to P of x, which we are going to show a proof. And also, what is the connection between Markov chain and MCMC? Okay. The connection between the MCMC method and Markov chain is pretty obvious, because every time we're going to adaptively change the Q based on the previous examples. In fact, it is in principle based on all the previous examples, but we're going to assume a first order Markovian property, so that given the immediate previous examples, all the other early examples are not influencing the next example. Okay, so this is actually forming a Markov chain, in the sense that all these states is going to form a Markov chain. And this probability is known as the transition kernel. Okay, and remember in here when we denote a x of a certain time point t, this x is not necessarily a single state. Okay, it is the state of all the variables in a model. Therefore, it could be a vector of many random variables, xt of 1 all the way to xt of say n. And what is that? You have a graphical model with many nodes, and this one slide is basically the entire set of values, okay, sampled at MT for the graphical model. Okay, so it can be a vector. And also, we are going to assume that this transition kernel is known as homogeneous. Okay, it's a homogeneous MC, meaning that the transitional probability isn't changing over time. Okay, and therefore we can simplify the notation a little bit and directly call it a T of x prime given x. It's a transition kernel. Okay, it is invariant. Okay. Let's see. So what's the effect of having a transition kernel conditioning on a older example? Okay, that basically move the distribution from a older one to a new one. Okay, because it's basically a transition probability or conditional probability conditioning on the older examples applied to the older distribution that defines the probability distribution of the older states, pi, right? And then you are going to marginalize over all the older states, basically remove the assumption of where the older states is, just in the exam where the whole distribution is moved toward under all possible older values of x, and that leads you to a new distribution. Okay, p of pi t plus 1. Okay, and this x prime is just a new notation telling you that this is a new state comparing to the old state x. Their range and the possible values are the same. Okay, so then if this is basically what this transition kernel is effectively achieving, and in our earlier statement about MCMC, we say that we are hoping for a protocol that generates samples coming from our target distribution. What that means, every sample that you draw at every time point at least need to come from the same distribution. And then that same distribution should be the target distribution, right? So let's first establish that it must come from the same distribution, how that can happen. Well, that means that there must exist a stationary distribution which allow this to happen. So that pi of x, after a transitioning due to the transition kernel should lead to a new distribution which is identical to the starting point. Okay, and that basically defines some conditions for the T. Not every T is allowing such a stationarity. Therefore, you need to have a kind of a special T, okay, that defines a stationary distribution. Now let's see when stationary distribution should happen. So there are some concepts which I'm going to state here, and they, at the high level, characterize the property of such a stationary distribution. But I'm not going to mathematically, derive all these facts. The first property you can just kind of get by intuition. Okay, why this is important? The first property is called irreducibility. Okay, a Markov chain is irreducible if you can get from any states into any other states in finite steps. This is very important because when you sample, you don't actually know where your new sample is going to be, and then that will be the stepping stone of newer examples. You want to make sure that regardless of where I, step, on the new distribution, on the new state, it will lead me to any other possible states under this distribution, infinite step, right? That basically at least allow the coverage to be realized. That in the end of the day, my collection of samples can legitimately cover all the possible examples under this distribution. So this is basically what the irreducibility is guaranteeing. The second one is aperiodicity, meaning that every move from one state to the other state is reversible. You can come back. Okay, there are two ways to come back. One is directly jumping back. The other is to go a long detour and to any other states and eventually come back. And that basically is periodic. Here we are talking about aperiodicity. And ergodicity is another term which is really referring to the joint of these two conditions. A MC is ergodic if it is irreducible and aperiodic. Okay. And this is important. That's basically the kind of key characteristics that you expect to exist under this transition kernel. In this transition kernel, you want the capability of moving into any possible other states, right? And also the ability to jumping back and forth between two states. Okay, so let's see how what kind of transition kernel T can satisfy this condition. Okay. Well, this is an important condition that it can satisfy. It should satisfy, called reversible. A Markov chain is reversible if there exists such a distribution, such that under this transition kernel, you have a condition called a detailed balance that can be satisfied. It means that if you start from X, okay, and apply to a transition conditioning on X, that will get you to a distribution that is the same as you start from X prime. Okay, X prime is just another state different from X that is in the range of the X, and the transitioning using the kernel conditioning on X prime instead. Okay, so that's called detailed balance. And when you have a detailed balance, you actually, which defines a reversible MCMC, then you can show that it always satisfies the so-called stationary distribution. Okay, this is a simple proof. You start from a detailed balance, and then you apply, a summation operation or marginalization operation over anything, over X or X prime. Either way is fine. In this case, we summarize a sum over X. Okay, and in here, you can remove X into only transition kernel, And here you have to include both, and then you get this part. Okay, so this is the very definition of stationary distribution. Okay. Okay. And recall that in MCMC, we just talked about an algorithm called Metropolis Hastings, right? It basically makes use of a proposal distribution Q of x prime given x, and then also a acceptance operator A, and the combination of these two is basically defining the transition kernel. Okay, and remember this is not a continuous function. Basically, it's a piecewise, right? You have this part and also this part, and it's also very interesting that you have some, if A smaller than 1, you actually could, really. Okay, so if A is smaller than 1, basically A equals to what? P of x prime, Q of x given x prime, P of x, Q of x prime given x, right? If. That basically also means that the opposite, the inverse of that is greater than 1. And if this is greater than 1, then A has to be equal to 1, right? You are going to use this trick to basically do some additional calculation to show that this transition kernel allows you to prove also stationarity. Okay. Okay. So you just assume a condition that this one smalls to 1. Okay. And then the reverse equals to 1. And you just plug in this into both ends. You get the A here, and you don't get the A there. A here equals to 1, right? And after a few steps, you can now reconstruct this part in here and reconstruct this part in there, and then you get the detailed balance. Okay, resultant from T equals to Q times A. Okay, so what do we get? What we get is that the Metropolis Hastings algorithm is going to define a transition kernel that satisfies detailed balance. Okay. And also, even more interestingly, you have the P here. That means that the detailed balance happens to your target distribution, not to just any other random distribution. Okay. So we basically have one stone on two birds. Because of the way we define proposal and the acceptance rate, we established a detailed balance situation, okay, which allows the target distribution to be the stationary distribution, okay, and the transition kernel to be defined by the moving proposal times the acceptance rate. Okay, so that's MCMC algorithm and the theoretical guarantee of its correctness. And then some caveats. There is no guarantee as that theorem saying when this occurrence will happen, or when this detailed balance or this stationarity will happen. Okay, it basically said that after some time, when your distribution is coming from the true, it's not going to move away from the true distribution. That's basically what detailed balance is telling you, right? But when that happens, it's basically depending on the heuristic situation, you need to have a burn-in to start from some awkward situation, which will gradually pull you into the detailed balance. And knowing how to halt this burn-in is actually a mystery, because there isn't a other than a few examples, I think there are some few very simple examples in the discrete case. You can prove the condition, the sample complexity. Otherwise, you have to rely on heuristic. Okay, so that's MCMC. Now I'm going to quickly move to another algorithm called the Gibbs sampling, which is a more operationalizable special case of MCMC. Okay. So in MCMC, basically, the process goes like I'm going to start with x1, and I'm going to go, all the way to xt, using a q of x prime, x, and also, a of the acceptance rate. Okay, this is doable. It is applied to all possible distributions. Of that basically leads you to the p. And what the Gibbs distribution is sampling is going to do is a simplification, or maybe a special case of this process. So here is how it looks like. Now let's take a detailed look of how the first stage looks like. Okay, this stage looks like a whole vector of states, and okay. Now, when I'm going to sample the second point, that means I need to basically get a new value for all the positions in this vector, right? And now I'm going to, you can use a q basically to propose, x2 given x1. That's basically how you're going to do it. It's a vector conditioning on a huge other vector. I'm going to use a very special q in this case, which allows me to do the following. I'm going to now copy everything up to here, right to there. Okay, so this is going to be my same x2 1. This is 1, by the way, time 1. Okay, and so all the examples except the first one is going to be the same as my previous example, except now this one is going to be replaced with a new sample. Okay, and what this new sample is coming from, this new sample comes from a conditional distribution of p of x1 given all the from the previous time point. Okay, so that's basically my proposal distribution. Okay, I'm going to basically sample the next example such that they are all but one dimension different from the previous example, and that different dimension is going to be sampled, based on a conditional distribution that is conditioning on all the other dimensions that I have sampled from already from the previous examples. Okay, and this one, of course, can get some further reduction if you recall. In the graphical model, the conditional distribution of one random variable given everybody else is what? Given the Markov blanket of 1, right? Or the neighbors, depending on what model you're using, graphical Bayesian network or Markov random field, you can always exclude most of the examples and the conditioning on only the blanket. Of course, I can go even more general. P of xi given mb of xi, because I'm going to, in the next step, X3, choose one of the other examples to be resampled and choose the remaining to be kept. Okay, so this is basically Gibbs. It's just a specialized way to draw the next example where you only change one dimension and keep the other, and you condition it on the other to draw that changing dimension. Okay, so I said this already. And there is an interesting property which I'm going to show you maybe later. This proposal leads to a which is always equal to 1. Okay, therefore your transition kernel is going to be only that conditional distribution of one random variable conditioning all the others. And sometimes people want to use another nomenclature. So remember, this time your time step becomes a little bit finer grained than what we experienced in the original MCMC. In the original MCMC, we say you have one slide, now you have a new slide in the next time step. In here, we are a little bit trickier. We say the next slide, even we symbolically call them the new slide, only one dimension is different from the previous one, right? And you may want to prefer to set another milestone. What if I eventually, starting from here, and after many steps, I had every dimension being replaced? Okay, you could still call every step to be a new slide, but sometimes people call a moment where every dimension in the slice to be replaced to be an epoch. Okay, and that's you can also call that to be another specialized tick, like t plus 1, where the whole thing gets refreshed. It's up to you. In the computing implementation, it just amounts to a different way of indexing the states. Yeah, but operationally, it's totally legitimate to call this xt, x2 to be the next state, even though it is only one-dimensional different. Okay, so just to maybe watch a few examples to see how they operate, right? So let's say we sample this network. We saw that before. And in the past, remember in our example in the last lecture, we have some difficulties, right? If you draw just examples using the trivial methods, you are not going to have many effective samples. And then in the end, we have the importance weighted example where we set evidence in and we chop this whole network into sub-networks, each of them giving you a particular example to be reweighted. And here we have a new idea. You start from time 0, which is a random guess of anything, or maybe an intentional starting point, like of or f. And then what you do is to basically define, the one states B, for example. You're going to only sample that and copy everything else. Okay, and then what you do is to conditioning on its Markov random field. B, the Markov random field is A and E, therefore it's only here. Then you can plug in, the A and the E into here, and then compute the proposal and draw sample accordingly. And then next, you're going to choose another example, another dimension E to sample from. Again, you can plug in now. This green stuff basically are the current context of the example. Okay, you plug them in and you compute another proposal, and then you sample the E like this. And likewise, you can now go to another dimension. You now have a new context with this green stuff, and you're conditioning them on, and then you finish one swipe, and then you go further, right? So that's basically Gibbs sampling. Sample, dimensions one by one, conditioning on the others. It's just making the whole business simpler, because usually we are very good at writing down the conditional distribution of one random variables given its Markov blanket. And then, it becomes a much simpler proposal distribution, versus a high-dimensional proposal of all the states. And then, we already claimed that the acceptance rate is always 1. Therefore, you are going to make use of all these examples. The real kind of overwhelming appreciation of Gibbs in the world of machine learning is tightly associated with this paper by Tom Griffiths and Mark Stiers. This paper was published maybe a year after the first, David Bly published the LDA paper, the topic model paper. Remember, in the original topic model paper, what technique was used to do approximate inference? Can you speak up? I heard some answers which sounds right already. Variational, yes. And we have 2 variational methods, but which one they use? A mean field approximation, right? Which basically is kind of factorizing the whole joint of all hidden variables into a multiplication of every single random variable, a hidden random variable, given some variational parameterizations, right? And we know that mean field is an approximation to the true. Therefore, it's faster, but it's approximation. Then this guy, proposed an algorithm based on Gibbs, which is no more complicated than variational mean field, because it's also allowing you to sample every one single random variable, or manipulate with every one single random variable, now with samples rather than with a closed form estimation of their approximating parameters. And then they just iterate this procedure over all random variables, like this one. In fact, they didn't even sample this one and that one because these are continuous random variables, which can be a little bit harder to sample from. Then they use a technique. I mentioned a keyword last time, but I didn't show how that technique works, which is known as the raw molecular valorization, right? You basically can integrate them out, okay, if you choose to. So they integrate these latent variables out and leave only the z to be the hidden variable to sample from. So they basically are going to only, produce a sequence of examples, using this proposal distribution. And this proposal distribution can be actually computed fairly easily, okay? And this is a closed form they provided, which, the form maybe is a little bit hard to decode, but you kind of see they are corresponding to 2 types of weighted counts multiplied together, okay? And this weighted count is so-called the word topic terms. It basically tells you the number of words, appeared under a particular topic versus all the words. That gives you the topic-specific word frequency, which can be counted if you know the z, okay, based on the previous examples. And this one is the so-called document topic terms, which gives you the counts of how many documents belonging to a particular topic, which again can be calculated using the z, because once you have the z in the indicator function, you actually could also estimate the topic counts. So with all these counts, n basically calculated from the z, you are able to by the way, this z, these 2 type of n's can all come from z of minus I, okay? And you can basically write down this proposal, okay? And here I have specific information about what these specific numbers correspond to and how they can get computed from the z's, okay? And then the algorithm runs very, very easily, right? So you are going to have this as your data. Basically, these are the indexed words of every document, okay? And up to here, you have document 1, and up to here, you have document 2, and so forth. And your z will be just indexed. Z, in fact, in here, I simplified the z to be only 1 index, but it's actually 2 index. It's the z of i's position and document j. Okay, you basically are going to index that like that. And then what you do is to assume that in the beginning, everything is given already. Okay, iteration 1, everything is given. due to a random initialization. And in the next, you ask what is the first word of the first document? What the topic of that word is. Okay? And how do you determine? Well, you use basically this proposal, which is the conditional of one single word given everybody else. And here is a closed form expression of that proposal, which is a multinomial, right? And then you are going to, conditioning on all this, which is in here, draw this new example. And it's 2 in this case, okay? And then you start the second position, which is now z of 2 given 1, document 1, okay? And the magenta stuff are everything that you already are given, which was from the previous time step. And you draw it, and you move on, right? And yeah, up to here. In fact, we are about to draw this one, for example. If we were going this far, then this is basically the z of 1 and document 2, right? So the indexing basically needs to be very carefully maintained. So if you see larger scale topic model implementation, it's usually a very, very sophisticated indexing program that allows all these z's to be stored and retrieved in a very efficient fashion. You're thinking about billions of documents and thousands of words every document. Then the storage becomes an issue. How they actually read all the rest of the stuff, in every sampling step becomes a bottleneck. Then how can you aggregate intermediate sufficient statistic? How often you communicate becomes a whole space of new problems. But this algorithm is extremely simple and liked by many practitioners. And in fact, it's getting so popular to the point that people start to augment the topic models with other priors and other stuff, like I have maybe additional functions like a sentiment indicator, which is overloaded on topic. Therefore, your z becomes I as the word index and D as the text index, and maybe a sentiment as the sentiment index. You can basically have a word indexed by whatever many way you want. Okay, you can still sample the same procedure. Basically, the same algorithm kills all these different designs. That actually starts the space of a lot of variations of topic models. Yeah.
So this is inference using data sampling.
Mm-hmm.
So how do you do learning?
Learning, if you actually remember, learning in the case of fully observation data is a maximum likelihood estimation. You can do learning anytime in here because you have the inference, the sample gives you the value of those hidden variables already. You are now dealing with basically a set of sufficient statistics, okay, of your model. And the sufficient statistics correspond to the mean parameters and canonical parameters naturally, right? So learning, basically, in fact, in the community of statistics, there isn't this word called learning. Everything is inference, okay? It's about estimating the random variables. And whenever you want to estimate the parameters, you just collapse the random variables, their instantiations, and calculate their sufficient statistic. Okay. Just like how do you learn Gaussian? Okay, you sample enough Gaussian examples, then your mean parameters is the average of the samples, right? Okay, so that's how Gibbs sampling algorithm works, and you see 2 examples, and this is a quick reminder of the theoretical insights behind it, right? We have now a transitioning kernel, a proposal, which is literally defined in this way, very simple. You can see that in principle, your new state is this whole thing, the whole collection of x, right? xi and also xi complement, the whole thing. And I turned it into as simple as just proposing one X. Okay, and keeping all the other X, the XI complement to be the same as before. Right? That's the one reduction. And also you can compute this acceptance rate. I'm not going to walk through the math. You can show to yourself that it is equal to 1. Okay. All right. So we have two algorithms with proper theoretical justifications of their correctness. And there are some practical issues still, right? How do you assume that even this adaptive kernel is good enough? When to stop? And here I'm going to say a few words on each issues. So in here, again, the quality of the queue can still be measured by the acceptance rate. And people usually struggled by having a highly pointed and narrow proposal, which is usually simpler to sample from and has low variance, or having a kind of a flat proposal, but it is going to give you a lot of rejections and make the sampling chain very slow. But it has a better chance to cover the whole complex distribution. The truth is that you don't actually know these two distributions. Therefore, all you are having is to blindly rely on the samples produced by Q to actually determine when to stop. In this Q, it may mislead you to be stopping very, very quickly because it is giving examples which are highly kind of concentrated. It never covers this region. Therefore, you may never see here. Therefore, you may actually conclude that you are already converging. Therefore, people are worried about this risk. I don't know the truth. I was told that I'm converging, but am I really right? Right? So people want to say, maybe I should explore a little bit more to have a more wider distribution. But in that case, it becomes slow. After I sampled, say, 1 million samples, I still don't converge yet. Something wrong with me or what? Right? So that's the struggle people always have. Therefore, you have some guidelines. Typically, people want to have a proposal which gives you at least a 50% acceptance rate in the MCMC case, so that you can keep half of the examples. And there are also some other ways to qualify the usefulness of the example. One is called the autocorrelation, computed in this way. By the way, MCMC examples are always autocorrelated because you are using the previous example, to define a transition for the next example. Therefore, there are correlations. This is different from the MC procedure where we have uncorrelation, which is a good thing because uncorrelation means that every example are equally important after their reweighting. But in here, when samples are correlated, there are formulas allowing you to compute the so-called effective sample size. For example, if two examples are just completely correlated, say the next example is twice the first example in magnitude, do you get two samples? You actually get just one sample, because there are no more informations out of the second example other than a linear scaling, which could be due to some other likelihood, some other constants. And so you want to compute the autocorrelation to make sure that you have a curve like this to ensure you or to basically encourage you using the good proposal. If you see a anti-correlation or autocorrelation like this, you may want to change another Q. Okay. And the other is about convergence. And convergence is monitored by plotting some interesting statistics of the sample. For example, you just mentioned about learning, and you can do a tracking type of learning. You keep estimating the mean of the Gaussian if you want to learn the Gaussian parameters, and you just monitor how the value change. It may start from somewhere and gradually converge to a place. And if like this, if that happens, that means it is a good mixing. Okay. And by the way, in practice, when people do MCMC, people don't start with one MCMC chain. You start with multiple places. Okay. The reason being that you need to do a random guess at the beginning. You may guess wrong. right? And what if you guess wrong and it doesn't get you to the right place, right? And also, you lose the opportunity to compare different trajectories and determine whether they all converge to the right place. So, for example, here you have a good mixing, meaning that all these different colors are kind of converging to the same place. They oscillate. That's mostly like a noise, but they are roughly giving you the same mean. But in here, not only they didn't get to the same place, but also they themselves are still highly kind of varying. Therefore, you want to either keep sampling or you want to try some other proposals. And another thing that you can do is to compute the likelihood. Remember in my opening statement, I said that all this MCMC or MC approach leads you to calculate the likelihood of the data using all these sample values. And you can track the likelihood. If your sample are becoming, converging to the true distribution, your likelihood is likely to be the best. Therefore, they should, platoon in some places, in these cases. Okay. So that's typically what people do to diagnose a MCMC. And then you can determine basically the convergence, when to stop burning, when to declare success of the algorithm accordingly by monitoring all these curves. Okay, so here's a quick summary of the MCMC. On the basic part, the key points is we're going to now, use an adaptive proposal, okay, and you are going to also have choices of further engineered adaptive proposal to be a conditional distribution of a single random variable given the rest, and by using the Markov blanket concept, you can make that simple proposal very, very easy to manipulate, and also get a constant 1 acceptance rate so that the sample can be better used. And then you need to also take care of some empirical aspects such as convergence, equilibrium, good mixing, and so forth. So with that, I want to, any question at this point on the basic MCMC technique, Metropolis Hastings technique, and the Gibbs sampling technique, so forth?
In Gibbs sampling, how do you choose which component to sample next?
Oh, good question. Yeah, how do you choose? He was asking in Gibbs sampling, because you are going to sample one random variable at a time given the rest. How do you choose that one? Yeah, it's. I don't think there is a very concise theory behind it. Typically, people either randomly choose, or people just follow a fixed order. You have the documents, right? And you just start from word 1 and go all the way down to the last word of the last document. Yeah. This actually has a computational convenience because the indexing is easier. But if you do random sampling, if you have a large data set, every time you change the index into anywhere into the middle, that actually costs you more clock cycles, in the actual implementation. Yeah, yeah. But again, there isn't a theory behind that. Yeah. Okay. Okay. So if no more question, let me maybe add a little bit new ideas into that. One of the struggle people had with all MCMC method is this behavior called random walk behavior. Okay, for example, here you have a target distribution which is skinny, oriented Gaussian distribution. Okay. And you want to start with a simple proposal, using a symmetric Gaussian distribution with a limited bandwidth. Okay. You could ask, why don't I use a bigger one? Okay, that's there's a cost. If you have a very big Gaussian proposal that has a wide kind of a variance, you're going to have a low acceptance rate and so forth, all these other behaviors, right? So typically people start from here. So suppose that my previous example landed me in here. and therefore I define this proposal here. I basically could have a new example anywhere in this. It could be in this direction, it could be in that direction, it could be in this direction, it could be in that direction. Basically, it could be anywhere, right? Every place has a equal chance of getting example. If you knew this whole thing already, do you have a preference of the direction? Okay, so basically what I'm trying to say that this proposal, okay, which is already anchored by the old example. In fact, by the way, the older example is useful in anchoring the proposal already in the right place. For example, if I have a multimodal, right, and by having the proposal anchored in here, it's already a better choice than my original x0 in here, right? But even you're anchored in here, you still have the next example to have the possibility of going here or going backward here. Now, which direction you prefer to go? Any intuition there? If you knew basically the true distribution, I bet you want the next example to go this way, not that way, right? Because it allows you a better chance to cover the other modality and define a proposal that is even more aligned with the new modality and so forth, right? And that's basically a preference or a bias against this random walk behavior, okay, defined by the proposal. All the MCMC, vanilla MCMC is a random walk based on the proposal distribution. But you want, hopefully, a behavior that is more directional, okay? So, for example, in this case, how can I kind of bias the sample so that it goes to this direction better than the other direction? Yeah.
You get the derivative of the and bias towards going in the direction of the
That's a good thought. The only information that gives you some sense of the rationality is the derivative, right? Derivative maybe of the likelihood function, and then you go there. Okay, so how can you basically impose that derivative into this proposal in a mathematically elegant fashion so that you can still prove convergence and correctness and all that? I guess one empirical idea could be I'm going to sample and reject. If I sample and then I plug in and find that it is correspond to a derivative higher than the derivative in here, then I take it. It's a very awkward procedure, right? So that leads to a new technique. In fact, not a new technique, but a technique new to the machine learning community as the Hamiltonian Monte Carlo. I guess people here probably heard this word before, right? What is Hamiltonian physics? It was taught, I believe, in college physics, if not in, I don't know which 16th grade, high school, I don't know. So here is the story. So Hamiltonian basically is a term given to the sum of what is known as the potential energy and the kinetic energy, right? So that's in our physics literature. And there are some interesting connections between the two terms and also the derivatives of Hamiltonian over two parameters. One is the velocity position, the other is the momentum of a object. We're not going to review physics here, but let's see how this idea leads to a new sampling method. So at a high level, here is the idea. I'm going to sample this target distribution. Okay, and now you say that what if I want to leverage on some gradient methods? Okay, I have no idea yet, but let's keep this in the back burner. And how about we are going to use a auxiliary distribution? In the past, what we do is to really try sample fewer examples or fewer random variables, like this raw black correlation method. We integrate out random variables. And in the Gibbs sampling, we choose one and the conditioning on the other whose value was already given in the previous samples. So in here, we do the opposite. We're going to introduce more random variable and therefore define this distribution. Okay. Therefore, in addition to the energy term we had before, we have a new term, K, which we call kinetic energy. Okay, so now back to some maybe nomenclatures in the Hamiltonian dynamics, right? We are going to have a position vector x and a momentum vector p, and then by the physics literature we have the potential and the kinetic, and the Hamiltonian is the sum of that. The key in the Hamiltonian dynamics is this very interesting set of equation. Okay, the derivative of the partial gradient or partial differential of the Hamiltonian over p equals to the derivative of x. Okay, the gradient of and the velocity of the object. And likewise, you have this other set of equation, the partial differentiation of Hamiltonian over x equals to the derivative of p over t. Okay, I have to change the notation a little bit by replacing the x into q, just because some of the materials I adapted from the literature use this notation. You can find those notations, the literature from our website. It's written by Ralph Neal and David McKay's book, on statistical physics and information theory and machine learning. Okay, so there are some examples. If you define Q and P to be like that, if this is actually one set of definitions that satisfies this Hamiltonian dynamics. Okay, again, the whole point is not about reviewing the physics literature. It's about basically defining, okay, the change of your state, okay, versus the gradient of a loss function over the change. Okay, so that's the key insight. We talk about, for example, in our current discussion, we want to have a more biased move of the x so that it kind of leverage on the gradient, right? So maybe from here, I want to move to the next x, which is consistent with my gradient. And that basically gives you an equation where the gradient is in the equation and the delta of the x is also there. Okay. In fact, you can now use multiple methods to start computing, okay, the delta, in the state as a function of the gradient of the loss function. And this is called the Euler's method, which directly basically establish, the change in P. By the way, P is the momentum, and the change in the position Q, okay, as a function of the loss, the objective momentum. And there is another method called the leapfrog method. Again, all these details are not very important. There are multiple mechanisms, telling you how to do the update. Leapfrog is preferred because it alternates between the P and the Q to calculate the updates in a more fine-grained fashion, in a very controlled fashion, so that you can avoid behaviors like overshooting or undershooting and so forth. And that's actually evidence, on how the sample, converge to the true trajectory versus a divergent kind of path using the two computing methods. Okay, so with that, let's return to MCMC. We are going to now focus on a new distribution where even though Q is the variable of interest, we introduce auxiliary random variable P so that it allows us to define the Hamiltonian, okay, based on U and K. Okay. And this is the potential energy, which connects to our original variable of interest. Okay. By the way, here it is a Bayesian setting where we have both the distribution of the hidden states or the states of interest, and also a conditional from the data or the priors defined from data. And then here is the kinetic term. That is a auxiliary random variable. So what we do is that we're going to start from somewhere and draw the P from a trivial distribution. And then we're going to use the leapfrog to compute the next step, okay, Q1 and P1. Okay. And remember that in the Q1 and the P1, we actually have a way to incorporate the gradient. Okay. The U, remember, is in here, this guy, which connects to our likelihood function of the states. And therefore, the gradient of that is not directly involved in the proposal of the next step. Okay, you are going to use this to propose where your next Q will be at. Okay, and then you are going to also apply, a acceptance and rejection protocol based on the change of the Hamiltonian to take that sample or not. Okay, so this whole thing looks like this. Look at that. Okay, the acceptance rate is computed based on, the ratio of the Hamiltonian resultant from the older example and the new example. Okay. By the way, the example is a pair of Q and P. Okay. So here, the key thing is, again, I want to remind you that this part is directly used in making the proposal. Okay. And with all this setup, you can even prove that the convergence, is leading you to the true proposal, a true distribution of the Q, okay, that you want to sample from. Okay, clear about that? It's a technique of sometimes people maybe generalize this technique to a more kind of a broader set of ideas known as combinations of MCMC versus optimization. Optimization is a deterministic method which allows you to use gradient methods to drive to convergence. Right? Remember, in convex or non-convex optimization, the main technique is gradient descent, all variations of that, projection gradient, and so forth. Right? And then the main idea in stochastic methods like MCMC is to do sample. Now you see that in this equation plus this equation, this optimization technique and the MCMC technique gets combined. Okay, so it's a whole field that many researchers nowadays are moving into and try to develop new technologies. Okay, here are some comparisons, of a Hamiltonian MCMC versus a random walk MCMC, and you can see, a much better, convergence, on targeted distribution, which are either highly biased, or in this case, you have a much. This is a little bit hard to see here, but you can see that the mixing of this, maybe in here it's even better to see. The mixing of the samples gets better than a random walk, which allows high correlations. In here, the samples are highly correlated because this random walk is not powerful enough for you to move away from the first examples and basically keep you oscillating. But in here, you can follow the gradient and move away from the proposal and cover the whole distribution very, very quickly and gets you a better mixing and coverage. Right? And there are numbers even validating that the HMC versus random walk has a dramatic improvement in the acceptance rate. Okay. All right, so that's a idea that I want to share, where you combine optimization versus MCMC. And this one, known as the Langevin MCMC, is just like Gibbs is a special case of Metropolis Hastings. Here, Langevin MCMC is a special case of Hamiltonian MCMC, where instead of doing the leapfrog, you are doing even more sophisticated updates, okay, based on fine-grained second-order updates of the sampling states, okay, and they have some nice better theoretical properties. And nowadays, people, imagine that if you even know a strange distribution where there are constraints on regions that you don't want to enter, say a sparse model, a sparsification prior or some other things that allows you to impose specific constraints, then you could imagine that this type of optimization technique could be further augmented to have projections and other changes to make the proposal even more efficient. Right. So this is an area that has been pursued by a lot of recent work, and I encourage you to take a look if you are interested. So this is Langevin MCMC. I guess the high-level idea is really, in order to improve acceptance rate and for better mixing, you are going to, incorporate this type of optimization-based approach to generate better proposals. I have some other technique which I'm not going to have time to cover. MCMC, a variational inference method, actually also can be incorporated with MCMC. Remember, variational method is also an optimization-based method, right? It directly gives you the answer to an approximation of distribution, and based on some evidence. So, an easy way to benefit from this technique is that your proposal could be a variational distribution, rather than defining a Gaussian or a adaptive proposal. Typically, it's also a Gaussian, right? In this case, you could directly use a more structured variational approximation to a complex distribution to propose the distribution, and then do the same, Metropolis Hastings step, for example, for accepting or rejecting samples. Right? So people have been trying all these different combinations of sampling technique. So I'm going to stop here, which is a grand stop of our classical material in graphic models, with then graphic model representations in directed and undirected, with then exact inference and learning, with and without hidden variables, and then with then also approximate inferences. We covered variational and MCMC, and we are going to go no further in the classical literature. In starting from next lecture, in fact, this Wednesday, we are going to dive into the more modern literature, such as deep learning, such as other reinforcement learning literature, where we see what we learned so far as a foundation to justify or to explain modern techniques that is of broader applications. Okay, so Wednesday's lecture will be a very interesting one. It's very high level, but it gives you how all our variational inference technique, how our approximate inference technique directly leads to the modern formulation of deep learning, including the GAN models, the variational autoencoders, and all that. Okay, thanks.